Let's try another example to convert decimal fraction 0.1 to the corresponding IEEE floating point format. So obviously the sign is 0 and the integral part is 0. So here we type 0 point, and now these are mantissa bits. So what we do is just take 0.1, the fractional part, multiplied by 2, and print it right at the corresponding bit position, starting at the left hand side of the mantissa. Then we multiply it by 2, we get 0.4, 0.8, 1.6. Then of course we drop the integral part and take the fractional part, multiplied by 2, get 1.2, then 0.2 times 2, 0.4. And from here it becomes periodic, because we get this 0.4 twice in this progress, and we get caught in this loop now, so that it's just basically is going to follow this pattern, 0 0 0, then 1 1 0 0 1 1 0 0. So we can now just try to project these results to our mantissa, and this becomes this type of thing, and then we just follow this pattern 0 0 1 1 0 0 1 1. So I can just copy and paste it this way. So let's go ahead and normalize it. Obviously we just take this fraction and copy and paste, and I'm going to do this right here. Then I'm just going to duplicate it, because we're going to normalize right away. So basically when we normalize, our radix point has to move to the first significant digit in our fraction. And so here we just kind of like replace these zeros with spaces and add the radix point right here. So we need to add the exponent to the normalized version. So it's this multiplied by 2 raised to the certain power. And now we can count how many times we need to shift our radix point. And here we have to shift it 4 times. So basically we go from here to 1, 2, 3, 4 times. And obviously we're shifting to the right. And when we're shifting it from here to the right, it has to be a negative value. So this is -4. And you can see it in our handout, in our step-by-step outline. So the negative power moves the radix point to the right, and the positive power moves radix point to the left. So just keep this in mind when you're completing your normalizing of the fraction and adding the exponent. So our exponent is going to be essentially e equals 127. It's always 127 plus or minus what we have to use as our power. So this will be -4, which is 123. Right, so the result is 123, which is binary 0 1 1 1 1 0 1 1. Okay, so this is our exponent. And now you can see the reason why it's so convenient to store the normalized version. It's not only because we don't have to store the integral part of the normalized version, but also because now we have more space for our precision points. So here we can add more of this. So I believe 0 0 is where we fit into this format like this, right? So that's exactly the field, those 23 bits that we have to fill. However, there is one more. I'll just remove this to avoid any confusion. All right, so this is our mantissa, but there is one important thing. We know that 1 1 will be the next set of digits if we had more space in our mantissa to increase the precision. So we take a look at this value right here. And now if it's 1, we're going to round this to 1. So this becomes a 1 because this is where the rounding is taking place. So the actual value here is going to be 1. So this is how denormalized fraction looked like. Right? So this is denormalized. And now, of course, this is all normalized. Okay, so we're ready to go. Of course, sign is 0, so we can now try this bit pattern to verify if everything looks good in our floating point converter. So we're just going to paste this bit pattern here, get rid of spaces, hit enter. So this is now our proximity to 0.1, where we just started to do the work, and this is how it's actually stored. So this actually explains why, when we were doing our loop of 100 times, adding 0.1 to the original 0, we ended up, and this is the double version, the last version that we tried was the double, right? But this is the float result, and you can see that this is the accumulation, these values right here. This is all the accumulation of these extras, because that's the real proximity to which we can get, or as close as we can get, to actually storing 0.1 in our hardware using this IEEE standard. So we're done with this conversion, but there is something interesting to try. Notice that the double version is sort of like lower value than the one that we get when doing the computation with the float. So here, if we just try to change this last digit to 0, okay, and hit enter again, and you see that this time our value becomes 0.09999. So it's sort of approaching 0.1 from the other side, from the lower number side. And so this explains why, when doing computation with the double, we're getting this 9.9 as opposed to 10.0 with the float, because apparently in case of a double, the rounding ends up having a 0 at the end of this bit pattern in the Mantissa storage.